Hello everyone. We can wait for a few minutes and then start. In the meantime, if you guys have any questions, you can feel free to ask me. Okay, I guess we can start. I'll just share my screen. Okay, little recap from what we saw last class. And yeah, few things. You can interrupt me anytime. Feel free to ask questions. And yeah, let's start the class. So last class we saw how to use functions, namespace, right? We started first with hello world. Okay, then I put that whole thing statement with hello world. Okay, then I put that cout statement inside a function. Okay, and then and then this function is just a plain old function. Okay, which is outside the main function. Then we put the same hello inside a namespace, which we ourselves define as custom namespace, which is this one. Okay, there's a hello inside it. Okay, which is in. So if you try to print this hello, you get hello world inside namespace, and if you print hello, you get if you print this hello, you get hello world outside. Like basically means this hello. Okay, and then if you just try to print hello, we just for like checking where we're actually printing it. We just have it plain. Okay. Similarly, we can have cout itself also defined, okay, inside our namespace, so that we can call this function of cout rather than the one we use from standard cout. Okay. So as to avoid name collision, we do this uh, check. Okay. It's more like separation through namespaces. It keeps your functions that you define inside a nice little namespace. So that's the usefulness of having namespaces. You can use using namespace standard and keep going, but again, normally it's recommended to avoid because having the full complete name, yes, it makes it lengthy, but it is more readable, and that always takes priority. Okay, so try putting the full namespace and the function and so on and so forth, because then we'll actually be clear on what function you're actually using, as in where things are, everything. Okay. There are cases where for a small region of space, you can put it inside some scope and use namespace, let's say using namespace of some standard or something else. That's also okay, because you might have some very big functions and all. So very big names in that space. Sometimes people do that. And as we'll see later, you can also use something like keywords like auto, which will automatically take care of very long namespaces. Okay. And we don't have to, as such, write very big names. Basically, it sometimes is more readable to not have long names. So, certain cases, it is useful. We'll see an example later. Okay. Some basic functions like adding, and we try to print the sum itself. Okay. Uh, for loop, then we saw if statements. Okay. Then we also saw how to do operations. Essentially, you can do normal operations. You have to use multiplication for by star, minus sign, so on and so forth. Store it in integers, and or you can have Boolean data types also. You can use brackets to separate your expressions. Fine. And then you can also use ternary operator. Okay. And so on. And yeah, so the increment operator, the post increment or the pre increment, depends on the data type return. Okay. One of them returns the incremented value, another returns the the pre-increment value. Okay, just print them and check for yourselves. Okay. Another thing was this standard ENDL, which is standard flush combined with slash n. Okay, it's basically a new line. It adds a new line. Also, it flushes the data in the string that you're trying to print in the buffer. Okay, it flushes the whole buffer. Okay, and prints, and you get the output. The other thing is this angular brackets, right? Double of angular brackets. These are used for, sorry, these are used for bitwise shift operations, but they're overloaded. We'll learn about overloading, but you can think of it like same function, um, taking um, I put it taking multiple inputs, okay, sort of. Uh, Depending on the data type, it will decide which body to use. Okay, that's functional overloading. There, uh, essentially, yes, cout is also a function, and depending on, so this is also the operator. Okay, and combined with if the right hand side is string or integer or so on and so forth, so overloaded, and essentially it streams the bits that you're passing, okay, to cout, and he can chain it together with multiple strings. Can have many more, just this left, the shift operator, okay, left shift operator, and have many strings and then keep combining. Okay, right. That was, I guess, more or less what we saw. Yeah, and let's move on to the vector class. Yeah. So, right. First of all, there are some important data structures that one uses regularly in programming. Okay, which will be like uh, depends. You can have lists, you can have maps, you can have sets, you can have stacks, queues, right? So on and so forth. Like all these data structures uh, are abstract types in a way. Like you have some sort of an idea behind it, as in how does a list should behave like? It should be a collection of some data. And the idea is that a list should have data. If let's say I want to represent that list in C++, okay, a handy little class is already defined in the standard namespace, okay, in the standard template library is the vector class. To access that, the include you include the header file called vector, okay, right? And the representation of list in C++ is can be done by this vector. Now, now, yeah, thing is, you have this you have this vector now, right? What's some of the properties it should have? One thing is, at least in C++, you can't have, I mean, you can have different data types in uh, general, maybe in Python and so on and so forth. But thing is, in C++, it enforces that all the data types of every element in that list, okay, has to be of the same data type. That's what you define by, let's say, a standard vector. So this is called a template. Essentially, this is the idea that you are only going to store integers. Okay, so that's what you pass here, and then define the name of your vector. So let's call it capital A, and then in brackets we pass this size. So I'm saying I want 5 integers, so that's how the vector gets defined, and the corresponding memory gets allocated. Okay, you can also define the size as some variable and then pass that size here. Okay, you also can define a vector without any size. So it's just a declaration. There is no size yet allocated for this. Okay. The another idea is that vectors, this list should have data in contiguous, like the each data should be contiguously arranged. So if I have the 0th value, the next value should be in that many units. So let's say integer is 4 bytes. So if I start my vector at some point by giving some pointer, okay, the next 4 bytes should correspond to the first 0th element, okay. Then the next 4 bytes should correspond to the next element, so on and so forth. Okay. The good part about vectors are using classes like this, okay. So just so you know, this will cover classes and objects also, but the idea is that but the idea is that having standard vector like this, okay, the um, good thing is, sorry, I meant to say, if you have classes like this, okay, so you can use some member functions of this. A very useful member function is the resize function. Okay, so you can dynamically change the size of your vector. Okay, so you can have like 10, and then you can give very large values also. But remember, vector gets dynamically allocated, okay, on something called a heap. Okay, heap is the memory that is uh, that gets allocated on your RAM. All right. So there are two, you can think of it like types of memory, which we'll cover today. Also, stack and heap. Remember, vector gets allocated on heap, and you might run out of memory if you try to allocate too much of it. Okay, so that's something you have to keep in mind. Another thing is the useful function called size, which keeps track of the size of your vector. So it's, for this case, it's 5, and after resize, it becomes 10. So you try to print size here, okay, at line 10, you'll get 5. At line 16, if you try to print, it will be 10. Okay. The idea is that the size, as uh, it's evident from the name, it keeps track of the size, yes. But the important thing here is that just resizing vector is not a simple operation, as in it's an expensive operation, one should keep in mind. Because you have to sometimes deallocate the whole vector, okay, allocate the new memory, and then uh, set all the inter-member variables to the new values now. Okay. The allocation deallocation can be very expensive. That's actually one of the most expensive part about um, when vectors get initialized. Okay, so use that sparingly. As in, when you're trying to write code, resizing it too many times doesn't help. You might as well allocate a big chunk of memory and reuse that vector. Okay. Also, we saw something called capacity. So capacity is the allocated memory of a vector. Okay, but it's always less than greater than or equal to the size. Okay, the reason being, whenever you try to declare or like allocate a vector of certain size, it sometimes allocates a little more memory than that. The reason being, let's say you want to resize it too many times, so as to avoid allocation and deallocation, it will have that extra chunk of memory available in the memory. Okay, but you can't access it yet. As in, when you try to access anything anyway out of bounds, it will throw error. Yes, but that part of memory is still not accessible. Okay, so when you try to, let's say, double the memory, so that extra part, let's say it was already allocated, fine, then it will just have a very low cost in setting up the rest of the values. Okay, it's basically like it already has allocated the value, it just has to change the range. Okay, now the size will be the new size that you define. So to reduce the cost of allocation deallocation many times, capacity is usually that's what the idea is. Again, it depends on your how your allocation happens, or it depends on the OS. It might do it, but then again, it's better to not depend on this feature of C++ while allocating memory. Okay, it's better to avoid allocation deallocation altogether, like too often. Okay, then we see a normal for loop. Okay, just start with defining integer setting to 0 uh, until it is less than the size of a. Okay, then you have then till then you try incrementing it, and to access any element use the bracket operator. Okay, so this square bracket accesses each element. The good part about this is it doesn't matter what the data type is. So the ith element will always be accessed by just defining a of I. So each element here could be of integer, double, or any other custom data type even. Okay, all right. Now, okay, so here we're just setting it to the ith element as the value I, and then just printing it. Okay. Very similar thing. What you can do is have the same loop. Okay, but the equivalent thing is what I've written here. Essentially, what this bracket operation actually does is the way it is defined is something like this. is something like this. Okay, so the a of dot data, this one. Okay, what it does is this one gives you returns. Okay, again a useful function dot data, um, the function name data. So if you to access member functions, we use the dot operator. Okay, so the name of the object dot the member function with brackets. So this gives you the corresponding function. Similar for size, similar for capacity. Again, so data returns the pointer to the starting element of the vector. Okay, so this returns the pointer, and then when you do, then what we're doing is some pointer arithmetic where you're adding the ith value. Okay, now remember, for a pointer, when you're adding values, the way it works is, here I'll make a note here. That's it. The way it works is, let's say the a dot data is some value in uh, some value like 71234 something like that. Then, so this is in bytes, right? So the fourth will be, so like now the data type for a is integer. It already knows. So integers take 4 bytes. So the 4 it will multiply and then times I. So this is how the shift will happen. So to access the ith value, it will shift that pointer address. Okay, so a dot data accesses the address. Always remember, address or a pointer is just a number. Okay, it's a 64-bit integer, always, at least in modern machines. Fine. Um, so the idea is that it's just a number. When we say a pointer, it's an address, yes, but the address is always uh, indexed by some number. Let's say this is the number. Okay. Now to go to the next value, it will look like this. So plus 4 times I. It will shift by 4 bytes. Okay. From that starting address to the for the ith element. And why 4? Because it's integer. That's how we define it. If it was double, it would have been 8. So on and so forth. Okay. Now, now it knows which address to look at. Now you use the dereference operator. So this star, when you use against a pointer, okay, so this whole bracket thing, okay, it will return a pointer again. Now, after that, when you use the dereference operator, it you now this means you access the actual value at that address. Okay, whatever this address returns. Because the data type is integer, so it will now try to read an integer from that address. So it will take the next 4 bytes, read that as integer, okay, whatever representation rules it has to follow, fine, and then whole thing is now got accessed. We're setting that to I. Okay. Similarly here, then we're dereferencing and accessing. It's essentially the same thing, but written in a cleaner format with the bracket operation. Okay. Any questions so far? All right. We also saw how to like write file in a way, as in you can have the whole hello.cpp function, the file, and then obviously you have to have the main function. You can also write a main file itself with main.cpp function, okay, and then call these other functions from here by including them in your uh, main file. This is something very standard in what people do in C++, okay, at least in production and so on and so forth. So you can include the header file. Okay. So the header file will include all these functions. Fine. That basically means that it defines couts, hello, add hello, and so on and so forth. Basically to tell main.cpp that these functions exist. Okay. And these functions exist inside this namespace. But the actual body of it, you can find it when during compilation, the linking during the compilation. Okay, so which will happen when we try to combine main.cpp and hello.cpp to both, or compile them separately and then link them. Okay. Now, yeah, So, right. Let's since we saw about vectors, so let's look at arrays now. Remember, for C++, both are lists. Okay, the list data type, list data structure, but they have little small differences between them. So let's look at that. Okay, yeah. So first of all, I'll include the important header file for this. So that will be array. And as usual, we'll include the IOStree header file to access the input and output uh, streams. Yeah. So right. Always remember your C++ file code. Okay. Always should have the main function because this is what the C++ executable will execute first. So always have main. Then to define an array, you just do this. Okay. Standard array. Okay. Then it takes template, but compared to vectors where it takes only the input data type, arrays take both input data type and the size of it. And then let's say this also we call array. The name as A. A very important distinction between them. Okay. They already take the size as input to the template. We'll cover templates later, but the important thing here is that template values in whichever you pass, okay? And let's say I want to define this standard array. It necessarily requires two input for the templates. And anytime you try to pass anything to template, it has to be compile time constant. Okay, not runtime constant, compile time constant. Meaning, let's say I have this size as 15. Now this value is set to 15, yes, but it can this size can change over during my runtime. So like I can set it to I've set it to 15, I can set it to 5, pass the size here again. I can do that. So this value doesn't is not necessarily a constant. Okay, I hope the idea is sort of clear. Because this value is just defined to be integer, it just enforces the idea that the variable size will always contain an integer. What is that value? It doesn't really enforce. Okay. The value could be 15, could be 5 or 10, so on and so forth. Okay. Now, uh, another thing we looked at is, let's say, a scope like we had here. Sorry, excuse me. So let's say inside this scope, I define a value, okay, and it is constant for this period of the scope, let's say for the main function itself, or this small scope. Then you can sort of treat a value like um, constant, sort of, for that region, okay, because it gets destroyed. Anyway, it goes out of scope, okay. So that is one idea. The other idea is, let's say I define A and read it from some file, and that file is not going to change for the whole run of this program. Okay. Basically, the idea is that there is a variable which reads from a file, okay, and that file is just there. It's on the disk. And your program runs, it always reads from that file and then does some computation and then gives some output. So for the runtime, that variable A, yes, it is not, it doesn't know the value beforehand, but for the runtime, it knows. It's not going to change. Okay, so in those cases, you can have a runtime constant variable in that case. Okay. Here specifically, what we're trying to say is the value of 10 here, okay, it has to be compile time constant. As in, while doing this compilation, it has to necessarily know that this value that you're passing is known to the compiler at compilation time. You can do something like this. We'll also see another way of doing it. Okay, I'll maybe cover that after this. So let's say I just pass this specific value 10. This is okay because compiler then knows the value 10. Okay. So very important, compile time constants and runtime constant. The equivalent of doing the same thing so this is the C++ way. The equivalent of doing the same thing is this. Okay. This is the C way of declaring arrays. Again, remember, passing certain values here, okay, makes sure that you're allocating memory on the stack. So arrays get allocated on stack, vectors get allocated on heap. So what's the difference? Usually heap is the memory, that is the large pool of memory available to the program, and usually that comes from the RAM, the DRAM. Okay, it could be in is of the orders of gigabytes or sometimes terabytes. So that's a large pool of memory depending on the system, which what kind of memory you have. But the idea is that a large system like that has a lot of memory for the program to use, and for a programmer to access those kind of memory, you can use vectors. So what's the disadvantage? It is slower to use because it fetches the memory from the RAM to the CPU. Okay. Instead, if it was stack allocated, which array has, and it was near to the CPU, so which is like the cache, okay, so CPU cache, then it is much faster to fetch those data. Okay. Secondly, the important point here is that cache is still limited in size, so you can't have a huge chunk of data here. So 10 or something is fine, but let's say you define a very large number here, then you run into some issues called stack overflow. Essentially, you might have heard of stack overflow. That's what happens. You're allocating so much memory on the stack that it just spills over. Okay. So there's a limit to how much you can um, allocate memory on that. Okay. So that's something to keep in mind. Another point is basically this is the difference between stack and heap. Okay. Stack gets allocated on cache, heap gets allocated on RAM. On the RAM, you have large pool of memory for you to access. Okay. And you can dynamically change the sizes, allocate, deallocate, and so on and so forth. Okay. The same variable cannot be deallocated and like the same variable cannot be changed its size as on a web for an array because it is stack allocated. And the way stacks work, you have to deallocate the whole stack and then define a new variable. Okay. That sort of only happens when A goes out of scope. So the same variable A, you cannot just resize it. Okay. Then another important point is, yeah, stack is fast, but lower in memory. Okay, lower in how much storage it can allocate. Heap is bigger, but relatively slower. Again, it is still faster than accessing memory from accessing data from storage or like your hard disk or SSD. Okay, which again is slower than accessing data from network, like let's say from some other computer. So that's sort of the hierarchy. You get latency, bandwidth issues, and so on and so forth. But again, each level has its own pros and cons. Okay. So this is the C-style way of allocating the same array. The usefulness of having array is that there is a boundary check, sort of. If you try to go out of bounds, it will throw errors and so on and so forth. The same thing with C-style array. Doesn't have really a lot of checks or something, but well, yeah. C++ basically makes the same idea in a more compact and gives the spin of object-oriented programming to it. So that's that's, that's the idea. That's the usefulness of using standard array. Okay, so let's look at how do we access it. It's pretty much similar to accessing vectors. So you define int I equals to 0, I less than. You can also do a dot size. Okay, You know the size a priori, but you can always use the variable for the same code essentially, a dot size and everything. Okay, the I plus plus. Then yeah, I'll just I think I'll just do the same thing. Yeah, we'll have a file. Okay, then set it to some values and then print. Okay, all right. Let's compile this. Right, that prints the values also. So size is 10. So I just store the same indexed value to it and print. So it prints 0 to 9. Okay. All right. In the same vein, let's so this is sort of a 1D array. Okay. What we saw. Let's look at a 2D array. Now, similar idea. As usual, we'll always include IOStream. Then we'll have the array uh, file. Then it's a name. So we'll define them. We'll define 2D arrays. Okay, in the C style way. So let's say I call it 5, 3. Okay. So this is sorry, 3 array. Then let's say I define it this way. Just 7. So this is a 1D array. Three will be 2, 8, 7. Right? So this is a 3D array. So these are some of the ways you can define some n-dimensional array. Okay. So to define, let's say n-dimensional array, you just have that many brackets and give the sizes in each other. You can essentially chain this, okay, and keep going and define your n-dimensional array. Okay. The obvious question comes, what about the size limit that you mentioned here? You said you can't exceed beyond certain limit, then you get errors and stack overflow. Exactly the same thing happens here also. It just so happens that a size of B7, like this 7, is 7 integers. Okay. Size of this one, can anybody tell me what is the size for A, capital A? Yes, that's correct. It's 15. Can you explain why? Okay. Yeah. Yes. Right, that's correct. To be more precise, the idea is that whenever you define n-dimensional array, one can think of it like let's say a square, okay, for two-dimensional. So the number of rows and number of columns is what you're defining here, right? So 5 is the number of rows and 3 is the number of columns. Okay, yeah. Another important thing is in C, arrays are arranged in row major form, okay, and the um, how do you put it? Row major form, yes. So the entries start like they go row wise. Okay. So the first row gets filled and then the next row and then the next row and so on. What I mean by that, I'll try to explain that. But the idea is that here 3 represents the number of columns, 5 represents the number of rows. Okay. So if you draw a matrix, the total number of elements will be 5 times 3. If you have a cube or a cuboid, okay, this is the slowest. You can think of it in any way, but think of it like the number of columns, the number of rows were there for a single two-dimensional array, and the height now is given by 2. Okay. So there is a plain sheet of matrix had 8 times 7, 56 elements. On the now there are two sheets. Okay, now in 3D, 3 dimension, just two. So the total number of elements will be just product of all of this. Similar idea, you can extend it this to n dimensions. Okay. And I'll also give you another picture for the same thing, but in how do we do it in C++? Right. I'll give it 5. So the slowest index first. Then plus plus j, j less than 3, j. Okay. This time to access each element, I'll basically write the same code that we saw here. Okay. Access each element and then try filling it. So this is straightforward. To access any ijth element, you just do this. Okay. Remember the rightmost index is the fastest index, rightmost bracket. Okay. So that's the fastest index for your n-dimensional array. Okay. And then towards the left, it keeps growing as then it becomes slower. What I mean by that. So this array means jth element. Okay. You access jth elements and for every ith element. So first you index all the j, this dimension, and then the I. So similarly, the same idea in a linear form is like this. Star three. So if you see this, and then let's say we try to print the same thing. Okay. So if you see, it prints exactly from 0 till 14. So 15 values. So the way I was able to do this is the so again you have to be a little careful here to understand, but it's quite simple actually. Remember, J is the fastest index. Okay. Uh, the way I've written it is the J index says okay the rightmost bracket. So that value gets accessed first. Fine. Then after this loop ends for j, then we increment in the next the previous to it. This bracket. Okay. So same thing you can represent in a linear form as this. So first I have the j values. Okay. Then plus the I index and Let's say if it was another element k, so then you write that's here it will be plus k and so on. And then each of them you multiply with the size before it. So j is the fastest, so no size for it. So just size 1. Then with I, you multiply the size of j. So with I, you multiply the size of j, which is 3. For k, you multiply size of 3. Well, basically this one. So size of 3 will be there, size of j, and then size of 3 is already multiplied, right? And then size of I also. So size of I is 5. You can do this recursively for any n-dimensional array. Okay. So there is no k here, so I don't need to worry about this part. But yeah, that's the idea. Okay. So this is the linear way in which you can translate any index of any n-dimensional array to a linear form. And mind you, in memory, in actual memory, this is how it actually gets stored. This is the layout. We do say it's a 2D array. We do say it's a 1D array. We do say it's a 3D array. But to memory, it's not actually represented in some cuboid or cube or sphere or square or something. It is always linear. Okay, because it's still an array. It's still a list data structure. Okay. Um, yeah, same idea we can do for this also. So let me just write that. Now I'll have 3 loops. Okay. So a k loop, which runs till 2. Before that, maybe I'll make I as the fastest and then j and then k. Okay. So the size of j is 8 here. So 8. Size of I is 7. So 7. Then we'll access here C. Okay. K, J, I. Fastest being I. Then J. Okay. So 3 indices I have I, J, K. Now I'll multiply the sizes correspondingly. I, you don't need to multiply anything because there's nothing to the left of it. So times 1. J times the size of I. So you see the size of I, it's 7. Okay. Then K times the size of this part, which is already has 7. Okay. So we'll write 7. Then size of J, 8. Yeah. This useful trick that I have just showed you. The nice thing is you don't have to worry about or get confused about sizes. It will always work recursively. Okay. So any n-dimensional, you can always write it this way. So now let's print this function. Sorry, the 3D array. We'll have k, j, I, c, k, j, I. Yeah. Any questions? Okay. So printing this, you'll see we get the values in a linear fashion. Okay. Yeah. So we start from C, we get 0, then keeps growing incrementally till 111. Okay. So this is all about ND arrays. Okay. 2D array, 3D array, so on and so forth. Okay. Now let's look at the same thing. Okay. But through arrays, like standard C++ array. So for example, I want to define yeah, a standard array of integers. Okay. Now you can just give the whole complete size for it. So let's say I want to write an equivalent for A. So it will be 15. Okay. So 5 times 3. I'll have the complete data here. That's it. Then uh, maybe call it D. Okay. So the idea is that D is exactly the representation that we have already here of A. Okay. But we're writing in a C style, C++ style array. Similar, very similar to that, but now we don't have to worry about any sizes or something. We just put 15 here, okay, and then same as here, but we don't have to even worry about indices. P of I equals to I. There's no need to index anything. It's the same thing, but written in a much shorter form, actually. Okay, and then we'll print this. As we see, the values also get printed in the same fashion as A, what we saw before. You can actually check A here also. Prints in the same way. So memory-wise, or how they get stored or accessed, pretty much everything. There is essentially no difference between A and D here. Okay. While yes, one is a C style, another is a C++ style. There are there's a different way of writing the same thing as you saw now, but feature-wise or accessing, uh, they're pretty much the same thing. Okay. As in, if you try to work with them, they'll pretty much give you the same performance in a way. So yeah, all right. So this is what an example where I linearize the complete list. So instead of representing in n dimensions, okay, you represent in just 1D, but basically uh, contract, okay, all the dimensions to a single 1D, one dimension. All right. Any questions so far? Okay. Let's look at. So this was the stack allocated array, and we saw the vector, which is heap allocated. Okay. Now let's look at the same thing, but how do we do it in C style or sort of the equivalent in C++? Let's just look at that. Like while vector does give you a very neat handy little thing, uh, let's try to see how to do the same thing and C++. Is there something you should be familiar with? So thanks. Okay. So what I'll do is I'll define a pointer A. Okay. Then start my main function. Did I return it? I don't return anything here, but for completeness, you can just add this return 0. Should I add that? Yes. Yeah, this way from last time. So this is something. Yeah. Okay. So write the main function now. Fine. So the way you allocate memory. So this is, remember, this is the statement, the line that I'm going to write. What we'll see now is how you actually allocate anything in C++. So you use a new keyword, okay? And let's say I want to allocate 5. So now the important thing is this new keyword allocates 5 integers, okay, on the heap. Okay. So that's the key idea here. The new keyword allocates memory and returns a pointer. And A is what we defined here. Okay, you can also do it this way. The reason I have defined it before is I can access it outside also. But anyway, nonetheless, we can also write it this way. Uh, so there are two, again, it depends on which, how to say it, notation you follow. Essentially for C++, both of these mean that you're declaring an integer pointer. Okay, so the pointer could be on the variable side or on the variable side, on the data type side. For C++, they sort of mean the same thing, but again, whatever you follow, be consistent. Okay. Um, yeah, just to avoid confusions later. All right. Um, I prefer this, so I'll keep using this one. So you can also do it this way. And let's say define 15. So I defined 15 new. I asked the code basically asks the OS, uh, give me 15, give me a storage with for storing 15 integers, and then I'll set that to B. Now B stores the actual pointer to the starting address, and for the same 5 integers, A stores the point. A is a pointer which stores the address. Okay. Fine. Now we can try to print these values, store and print and so on and so forth. Okay. So for A, it is 5. I access each value by just define I. Uh, this time maybe I'll just not just store I. Maybe let's go with like 2 times I. Okay. And let's print and say the same thing. Okay. So I'll compile and print now. Yeah, that works perfect. So what we did is we declared a heap allocated list. Okay. Here will be a chunk of memory which is heap allocated, and we did not use vector this time. A vector is a very nice defined class, but if you want to start from the first principle, you can also use new keywords. The usefulness is that new can uh, not just works with just plain data types like this. You can also use it for uh, in constructor and destructor. Okay, so corresponding destructor we also see. But the idea is that you can allocate objects for classes also. Like have a pointer to that allocated object. Okay, have a pointer for that and store it in some other pointer, custom defined pointer. You see those examples, but the idea, something to keep in mind is the new keyword allocates memory. That's essentially the idea. Okay, and returns the pointer to access that chunk of memory. To delete this, again, remember this was allocation of memory. A very good practice with C++ is always delete it. Delete the allocated memory. Because otherwise, if you do not delete a chunk of memory in the program itself, uh, that memory still stays allocated, okay, in your memory in your program ends. So then what happens is, let's say your operating system runs a bunch of programs, and each of them have some memory. Uh, they request some memory to be allocated, and they do not get freed. Your RAM gets full. Okay. Then after some certain time, you just get system crashes. Okay. Yeah. It's always a good practice to delete the uh, allocated memory. Okay. So to do that, we just use the delete keyword with a pointer, right? Okay, so far so good. Right. Next, when okay, no questions. So next we can say is the same heap allocation but through vectors. Okay. So this was the allocation in like a 1D sense. Okay, this is the same heap allocation. Now we'll look at how to do it. So this is again, this is a C++ way. Okay, there is a C way also. You use mallocs and free. Okay, for the same equivalent things. Can look that up for the same idea. But now to look at the ND array. Okay, so let's say I want to define an ND array. Right. How do I sort of represent that in vectors? Yeah, so represent that using vectors. Okay. So stream and include vector. Okay. And a main function. This time I'll just include the return first. Uh, uh, return. Yeah. So similarly, let's try to copy this. We'll write sort of the equivalent things here. Uh, Whatever we saw in ND array, 2D array, 1D array, 3D array, in terms of standard arrays, okay, like C style arrays here and standard array here, the C++ array will now do the same thing in vectors. So to do that, so let's first define vector. Okay, integer, yes. So first let me define the B part, which is 7. Okay, done. For the A, what I'll do is have a standard vector. Okay, this itself will become my template for another standard vector. Okay, I hope you get the idea. So this is this A is a standard vector. Okay, instead of taking integers or storing integers, it's itself stores standard vector of integers. Okay, so it's sort of a 2D array in the broader sense, but remember this is not a list actually. Like if you take the whole layout here, there's actually in memory still a list. Okay, where contiguously all the data, all the 15 data, okay, 5 times 3, 15, all the data were stored contiguously. But if I take this A here, excuse me, if I take this A here, this is actually a linked list. It's not a list in the general sense that it's contiguous layout. It's actually a linked list where A is a standard vector and each space itself stores or points to a vector. Okay, so you can imagine a linked list where you have certain spaces and each space, okay, points to another contiguous layout or some data. Okay, they themselves could also be pointing to some other data. All right, so that's sort of the idea we'll use for the next one to define C. Okay, so we'll take this standard vector and define another inside the integer. So this C now becomes standard vector of standard vector of standard vector of integers. So important thing to remember is while the C style ND arrays were lists in a contiguous sense, but if you try to do something similar in like a ND array sort of ND list sort of thing in vectors using templates like this, remember you still get, you do get the idea of three-dimensional or two-dimensional or n-dimensional array, okay, or list, but it is not continuous in layout. It is a linked list. Okay. To now, another important thing is here the memory was allocated. Here in these cases we haven't allocated memory. Here we have allocated memory. So to do that, you'll have to define some values. Let's say I define m to be 5, okay, and to be 3, and let's say p equals to uh, 2, q equals to 8, r equals to 7. Okay, now let's start writing loops. Integer I equals to 0, I less than, sorry, yeah, okay. Uh, so which one do you guys want me to resize first? Let's do A first. It will be simpler. So A dot resize, sorry. So the size of A is M, and like I just defined M as 5 and N as 3. So I'll resize it to, can anybody guess what I resize it to, M or N? Remember, when I resize A, so this resize, so forget the internal part. So this is the outermost standard vector. Okay, so the outermost standard vector is sort of like the least, the slowest index. You can think of it that way. Okay, so here it should be M or 5. Basically, this guy which I'm trying to allocate memory for. Okay, and then here, this is another index. Okay, to go over each size of it. So I can just pass size of A, I plus plus. Okay, then in a loop, I will take the ith element of I and then resize it, each of them, okay, to n in a loop. Now let's print this. I should actually get an error, so hopefully, yeah, yeah, compiles perfectly. Now this resizing is done. Remember, I can't set values like this here yet. I mean, until I allocate memory, and I've gotten segmentation faults. Okay, now I can try to put values and print it. Uh, that case, what I can then do is, yeah, let me just do it this way. Instead of A dot size, I'll give it M. Okay, here N, change the value to J. Okay, so A of J equals to J plus I times the size of J, which is N. Okay, now we'll print it, okay, using the same two loops. Now you might think Well, this is a little roundabout way of declaring the same thing and requires a little thinking, yes. But I would like you to point point you to notice this one. So essentially, we're getting a C style access. So we use two double brackets. Here also we do the same thing. Okay. All right. So that's sort of the idea here. You get the same way of accessing the data, but using them in a linked list. Okay. I'll show you a much simpler way of dealing with this. So for now, just so uh, you know about these things I'm showing you. All right. Let's print them values. Right. So as you see, it prints perfectly from 0 to 14. All right. Now let's take an example for the same thing, but this time it will be for the C. So 3 dimension. It'll be a little more complicated, but that's okay. Go to the example. Won't be as difficult. So outermost index is 2, which is P here for me. So I'll put P here. Okay. Then, oh, another thing, mind you, here I used A dot size, right? That's the size of A, which is M anyway. So you could put M here also. Like anything is fine. All right. Maybe I'll just put M. So that first look at M, then second time M and then N. Okay, so on and so forth. That's the pattern here. For C, it will also be similar. Okay. So you put P here, then resize C, okay, each I to Q. Okay, that's the second fastest index. So you resize to Q. I is to through till P, then another loop J, okay, which goes till Q, right? And then instead of printing here, because we're not done yet, we have to resize the ijth guys to R, which is 7 or this fastest index. Okay. So hence it requires two loops to resize the complete thing. And then finally, K, right? So PQ and then R. Now we will access the each individual element. Remember, here I is not the fastest index, is the slowest index. Sorry, is the slowest index. K is the fastest index, then the J is the fastest, and then I. Okay. So K, J, I. Okay. For K, no multiplication required. For J, we'll multiply with the size of K, which is R. Then I will multiply with the size of these two, this whole thing, which already has R. So R will multiply, and then the size of J, which is Q. Okay. Same loops now for printing. So C of ij k, C of ij k. All right. So let me format it a bit. Okay. So we saw how to resize a two-dimensional vector. Okay. In this way. So first you resize the outermost thing, and then you resize. First you resize the outermost thing, then you resize each individual vector in a loop. Then you can store values and then print them. For for a 3D array, for a 3D vector, you first again resize the outermost vector. Okay, so that's using P. Then we resize each individual vector, and that itself Ci is also a vector. So we access them using the J index. So remember, C of I is also a vector. C of ij is also a vector. Okay, so then we resize them using the resize function, and to each of them to R. Right, and then finally you have all these loops. So Now to actually access each element, so now Cij is a vector. So to access its element, you use the k index. Okay. And then you write it in this way. So kji indexed, and then finally print it. All right, let's print this and see. Yeah. So okay, hopefully no mistake made. So A of I we saw before 0 to 14 is what got printed, right? Then from C for C from 0 till it keeps incrementing till 111. All right. Any questions? So we covered arrays, heap vector. Okay. Right. Any questions so far? If you have any doubts, you can ask me, or I can move on to the next topic. Okay. Now let's look at something called a const. So this qualifier, okay, to a data type. Okay, 3D array is initialized. Oh, sure. Okay. So the question is about how 3D. So do you mean the standard vector way or the ND array? Maybe I'll just write it as ND. Sure, sure, sure. Uh, uh, I hope you understand the ND array part, how C style array happens. So this is a C style array. To declare this C, so the idea is like a cuboid. So first of all, in one dimension, you have 7, another 8, another 2. So this was actually values, which is in the layout of first 7 values. And for every 7 value, there are 8 such columns. So this was like, let's say, one direction. Okay, think of it like a line containing 7 values, and 8 such lines were produced, okay, in parallel. Then we get a matrix of 8 times 7, 56 elements. And then in height wise, we repeat the whole process twice, okay, to get a cuboid. Very similar idea. We'll do it for vectors. So a standard vector initially stores only integers. Okay, that's the thing about these templates. That very powerful actually. They don't just take custom data types. Sorry, they don't just take the inbuilt data types like integers. They can also take little more sophisticated complex data types, which is like a standard vector itself. Okay. And then you can keep chaining it actually. So like what I did here. Inside this integer, I put a standard vector of integer itself. Okay. So that's sort of the idea. Why does this even work? Okay. Because you can put this template as so that's you have to write the code actually, but the way standard vector itself is written in C++ standard, you can actually do this. Okay. All right. Now let's look at how this is actually done. So I'll put ND array on the side for us to compare. So first of all, let's look at A. A is of size 5 times 3. Okay. So the idea is that we will store 15 values. Okay. Okay. What I'll do is maybe I'll show a very simple way of doing the same thing. Uh, Standard vector of integers. I mean, it's not necessary that you do it this way. It's just a concept to learn that you can do this in C++. Okay. You can always do it the whole thing in this way. P of 15, like we saw here. Okay. And then print and store values, so on and so forth. Similarly, uh, A was 15, so C is 56 times 2, it's 112. And to access the ith element to store, you can just do the I. So here to access each element, we will have to, yeah, do it this way. So I, J, K equals I, sorry, I plus J plus K, and now we'll multiply each value. So I'm saying I is the fastest index. Okay, so I is for 7. So J is, so for J, I'll multiply the size of I, which will be 7. So 7 K times 7, sorry, 7 times, uh, sorry, yeah, so J will be 8. Yeah, size of J will be 8. Similarly, I'll just copy this thing. Okay. Essentially, the idea is that you have to write 3 loops, or you can actually write a single loop. Um, yeah, this is, I don't know why I complicated this way. Yeah, to do the same thing, you can just write actually a single loop. Maybe I'll just write it this way. Why I will comment it. I equals to 0, I less than 112. Okay, I plus plus, and then simply I, C of I equals to I. Okay, so I understand it looks, so the whole thing here, okay, right, is just replaced with these 2 lines or 2, 3 lines. If I include this line also, so yeah. So this is a declaration part with no allocation. The allocation actually happens from here to here. Okay, and for the same thing, if you try to do it in a single linear list, okay, and not do an ND array, it is just these 3 lines. That's it. You make an array of the total size, loop through the total size, store I with I. You actually don't need any of this. So, okay, it essentially means the same thing. It's actually also faster. Okay, I can repeat the how we allocate this memory bit if that's what you're asking. But I at least hope the idea is clear. When you try to store an ND array, okay, like in a single linear array, you essentially store the same data, okay. But the usefulness is that you don't have to worry about how you are actually storing it in the n-dimensional structure. Performance-wise, having a single uh, array is actually quite fast. It's actually the fastest in any of these cases, especially this one, because a linked list will have to jump from one pointer to the other. Okay, as from a one memory location to the other. Okay, but if you have a linear array like this, okay, it can preface data, the next data, and so on and so forth. And remember, in architectures or CPU hardware, this kind of uh, linear arrays are quite fast. Like the hardware is actually designed for it to be very efficient to fetch data when you're trying to access the next data, like data contiguously. What I mean by that is, let's say you're accessing the 0th element, accessing the next element or the element at 1 is quite fast, so on and so forth. Okay, that's the idea. It is cleaner, yes. Don't have to write all this. It's much cleaner to write it this way, just simple. That's definitely one advantage. Second advantage is of speed. Okay. Uh, I'll just explain this part since you're asking. So C itself is a standard vector of standard vector of standard vector. So actually, if I have 3 standard vectors, I have to have that many allocation. Okay. So if I have a single standard vector, I already allocated it here. If I have 2 standard vectors, I have to allocate memory for this standard vector and also for this standard vector. How do I do that? The first standard vector here, I resize A to be of M. This is 5. Okay. So this standard vector now can store 5 of something, of whatever this template is. So it can so now it can technically store 5 standard vectors. Okay. This standard vector of A itself can store 5 standard vectors. So how do I do that? But remember, each of these standard 5 vectors have not been allocated yet. So otherwise, if you try to do this A of ij, you'll get segments. So you have to allocate memory. So I loop over the size of M. Okay, so 5, M is 5 here. So those 5 standard vectors, I access each of them by using A of I. So 0, 1, 2, 3, 4, so on. So each of them, then I resize to the size N. N is 3 for me. So now each of the standard vector inside can store 3 of something. What is that something? Integers. So that's my template inside here. So this means you can store now your standard vector. Each of the AI standard vector can store 3 values. And how many of such AIs are there? 5. Sorry, 5. Okay. So this is essentially the same thing, like storing 15 integers, but in a 2D standard vector way. Okay. Now, same thing with C. Sorry, excuse me. Same with C standard vector. So first of all, we resize it to P. Okay. So that is 2. So that's the outermost index. Okay. So we want 2 of this standard vector, which can store standard vector of standard vectors. Okay. Next, to we have to, so this one we allocated the memory. Okay. For the second part, so like for this standard vector, we'll write a loop, go through the size of C, the outermost, which is P, and each standard vector, okay, C of I will resize to Q. So this C of I is now this standard vector, which itself, so C of I will be uh, allocating this one. Okay. Now this next level we go. We have 2 loops. Okay. We access C of I of j. So C of I of j will allocate R. As in, what is R? Now integers. There's that many integers it will allocate. So you can keep going for each level and then keep allocating memory. So similar idea, but in a 2D sense for now. And then finally, the final integers, we want to actually store the value. To access them, so C of I of j, then k actually accesses. So C of I, j, okay. So C of I will access this one. C of j will access this one. C of k accesses the integer. That accesses the integer, and then we store it in the linear way. Okay. This is some formula. You can think of it like formula to access elements in a linear fashion. That's all. That's the idea. This can work both as the index. This can work both as storing the actual value or as index. Okay. All right. Then finally we just print the thing and access them from the outermost to the innermost or the fastest index here, right? And then get the same value. All right. I hope the concept is clear. Okay. Awesome. Okay. So let's look at something called const. As usual, I'll include a string, okay, to print values and so on. I'll show the I'll show the way, or well, it is also available in C, of course, but the okay, let's not do that. Uh, okay, let's do it this way. I'll define an integer p. Okay, 7. Now this integer p, I'll define as const. Okay, so what this const does is it makes sure that whatever value you store in p does not change. Okay, so yeah, so this value, so basically it's like, so the variable P will always have the value 7. It's guaranteed. Okay, that cannot change for the whole program. No, that's what const does. Okay, it keeps the value constant when it's qualified for any variable. Okay, so to see the idea, we'll have the main function. We define, let's say m equals to 10. Okay, then define an integer. Okay, n, and then write uh, n equals store the address of n. Okay. So important thing to note here when I say ampersand, it means the address. Okay. All right. So m is a integer, yes, but it's actually stored in some place, right? In some memory. Now that piece has some address. So we get that address by qualifying it with the ampersand or storing it in n. N, remember, n is a pointer, okay, of data type integer, and this is also data type as m integer, so not a problem. In any case, it wasn't a problem if the data type was different anyway. The important point is that m is a uh, some variable. It has some address. We store that address in n. Okay. Now you could technically store any address here, and that n will treat it as an integer pointer. Okay, that's sort of the idea. But anyway, we'll come to pointers and typecasting later. But that's sort of the goal here. Uh, the goal, at least the idea here is that you get the address of m, store it in n. Okay, and because m is a integer, and then when you try to access, uh, let's say, uh, let's just print it, access m. Then also access n. And rather than write it as star n, as in I'm dereferencing n to access the value it has. Okay. Oh, sorry. Yeah. So both of them print 10. Okay. So the first value m is stored 10. That's clear. If you try to print m, it will print 10. Second one, might not be too apparent, but it's actually the same thing. So we have an integer pointer n, and we're storing the address of m itself. So if you try to dereference n here, okay, it will, what will it do? It will access the value stored at that address, which is the address of m, and that has value 10. So both of them print 10. Okay, I hope that idea is clear. Okay, next what we'll do is dereference n and then change it to 9. Now let's see. Okay. Oh, sorry, my bad. Yeah. So previously it was 10, but now both of them print 9. Even M also prints 9, even if I did not touch M here. So that's something you have to be careful here. Like, so that's the thing about pointers. What I'm saying is, and I'm dereferencing, okay? I'm saying store 9 in the address of N. So whatever the address you have, okay, of N, uh, so whatever the address you have of N, okay, you access you access the value there and put 9 now. And what is the address that n had? It was the address of m itself. So now m, which was 10 earlier, has 9. Okay. right? I hope this idea is clear. Now, we'll have a little twist now here. I, Earlier, I had defined const integer p equals to 7. Okay, can I do this? So I pointed to an integer here, n to integer. N was integer, fine. I pointed to an integer. P is also integer. Can I do this? Okay, maybe I'll not do it here, but the later line. Address of P. I guess since I'm asking, there must be a catch. So let's compile it and I'll show you guys. That throws an error. Okay, why? So can actually read the answer from the error itself. So we're trying to assign an integer pointer from a const integer pointer. Okay, so P, okay, was constant. Yes, that's clear from the constant keyword. But the if you try to do if you try to get its address by ampersand P, okay, you get something called a const integer pointer. Yes, because that's an address. But important thing is that address that we have here belongs to a constant place. Like the address, okay, itself is constant. The values that it contains, that address is constant and should not be changed. But but look at here, integer pointer. So here the constantness is not qualified, as in the n itself, if it accepts that address, okay, later on it can change the value like this. Because and it was able to do so for m because sorry for m sorry for m because m was not const qualified. Okay, so this is not allowed. Okay, something to keep in mind. You can't cast already const integer pointer to to an integer pointer or some data type. It correspondingly holds for double, float, and so on and so forth. But it's sort of the idea. All right. Okay. I hope this is clear. Another thing is um, to define constness, people also use the macro hash define, and then let's say I define um, number like this as a. So the idea here is that macros work in a little uh, strange fashion where wherever it sees the word number with capital letters, okay, it replaces them with 7. So that's the hash defined keyword. Okay. Important to remember, this is a preprocessor or a macro. This is a macro, okay. This comes under some a class of things, even hash include, okay. All these are preprocessors, meaning they execute or they get executed before even the compilation happens. Okay. So basically, so let's say hash include, it will copy the IOStream file completely in the line 1. Okay. And obviously from line 2 to line 21, all of these things will move down. That's all. The hash include header file basically does that. It does not care what does the IOStream file itself contains. It will just copy and paste it here. Okay. Similarly, the hash define, okay, number 7, it will find number like exactly this text anywhere in the code and just replace it. For example, if I have number here too, it will find number and replace 7 here. Okay. As you can guess, there is a danger to it. If okay, so the idea is that wherever you see number, it becomes compile time at compile time 7. So sort of like similar to this one, right? So compilation time, I had an integer here with p equal to 7, acting as 7. Compilation time, I had a variable p which acted like 7. Okay, now number also acts like 7. So in a way, this macro is also a compilation time constant and throughout, very similar to P. But a huge difference between them is that a macro is much more has caveats and it's much more dangerous if you don't use it carefully. So let's say I define like this P as 7. Okay. So then what actually happens is wherever it sees P, okay. So if I do control P, so you see these three places, it will replace all of them with 7. Okay. That's how macros work. So as you saw, I had 7 here. So let's say I define P. It will replace this also with 7. You can run into some huge problems. So for example, you define variables like MP. It will rename a variable as M7. Okay. So hence you always see macros being not defined with small letters or something because they can be used for variables. People always have take extra precautions with underscores, number, and then underscore to especially define that, oh no, be careful, my macro is always this one, which will be 7. Okay. So the underscore, especially because we don't usually define variables with underscore, okay, and capital letters, okay. So macros are always defined in this way. Okay, you can actually define it just P also, like I showed before. But again, you can run into issues. All right. So be very careful while using macros. Okay, sort of the same idea with having constness. Both of them have the constness to them, but one is way different than the other. Okay, all right. Uh, yeah, I think that's it. Yeah. But I guess we can continue next the next topic in the next class. I'll cover some ideas about. Oh yeah, we can start uh, references, how to do line inline functions, constructor. We'll basically start classes. Yeah, the main thing, the main idea behind using C++ is to have classes and objects. Okay, and those learning them is actually one of the most important parts about C++. So we'll look at that and some things related to those having classes, objects, constructor, uh, how to use. Also, I'll maybe cover a little bit about pointers and references both also to it. Yeah. Okay. With this, we can I'll end today's class. If you have any questions, you can ask me or feel free to uh, exit. Yeah. Okay. So, if there are no questions, then we can end the class now. Um, yeah, like it discussed, we'll cover classes, objects, some notes about pointers, references in the next class. Again, the advice will be to practice these questions, practice the concepts, so to get a better understanding. All right. Happy coding. See you next class.